Welcome to the dynamic learning hub of XLR at Andheri East. A prime spot conveniently located at just a 5-minute walk from LIC Andheri. Proudly trained over 2 lakh students.
All right. So good evening, everyone. Welcome to the session. Let us start. Let me share the PPT. Okay. All right. Good evening. Good evening. Good evening, everyone. Yeah. Okay. Let us start. Okay. So fine. All right. So good evening, everyone. All right. So today we are going to see a bit on attention mechanism. Okay. And why attention especially is for building an AI agent, right? So we have built a few, I can say very small AI agents. We have seen a very small AI agents built yesterday, and through coding we have done those. And let us first try to understand now that how these AI agents are actually done on a bigger aspect using the attention mechanism. Okay, so this attention mechanism we are going to implement today. Okay, so one of the most important attention mechanism is the sequence to sequence attention mechanism, and that will be done using Bahdanau's attention as well. So we can just try to understand that how this attention mechanism actually functions. Now, before going into the implementation of the, because most of the session today also will be a practical part. Okay, so only bit of theory to understand what is this attention mechanism. So I'm just going to tell you a few things on that. So on, the first important thing is to so the most important thing is to understand what is this attention mechanism. So especially when we talk about the attention in a critical way, to understand the term attention. Okay, so attention is nothing but keeping things in memory for a longer period of time. Okay, so that the context will be understood. That is what the attention, the meaning of attention is basically in particularly artificial intelligence. So when we talk about attention, it is very important that how using using a certain algorithms or certain mechanisms, especially how we are keeping things in the memory. Okay, so how we are actually keeping them in memory for longer periods of time. Okay, so that our analysis, will be, you can say the analysis will be in a very easier way, because things, you can understand like this, like, if things are in memory for a longer period of time, processing and accessibility of the things will be much easier. Okay, so what happens then is, the way, understanding the context, it might be, the way things function will be a bit easy. So that is on on that basis this attention mechanism actually functions. Okay, and one of the models is the sequence to sequence model. On that, we have something called as a Bahdanau's attention. So based on this only, a transformer actually performs, or you can say a transformer actually functions. Okay. Now, this attention addresses this by allowing the decoder to dynamically attend to different parts of the input sequence during the decoding part. This is what, because basically what is going to happen, we are going to do the encoding part as well as the decoding part. Now, let us see where these attentions are basically used. It is basically everywhere, everywhere, because all the AI agents, whatever AI agents we are actually building now, everything, like literally everything, uses this attention mechanism. So either they use the Leong attention or they use Bahdanau's attention. So because those are the two attentions which are available kind of right now in a transformer. Okay, so these are the two attentions which are being actually used. Okay. Now to understand these two, attention mechanisms. Okay. So it is very, very important to understand how these are actually done. Okay. Especially some key applications we will see how this is basically implemented and how this actually functions. Okay. So that we'll be able to, figure it out that how this particular thing can actually work. Okay, so it is in a very in a very easier sense. Okay, so it is very, very important, as that how actually things perform. So keeping in a broader picture or thinking in a broader picture, so the first important application is the machine translation. So this machine translation is a very important AI agent which is in function kind of right now in the real time. For example, when we are actually translating or using a certain machine translation, it is very important that we are going to apply a certain machine translation, right? So this machine translations, for example, whether it might be Google or some other, this main focus is applying the attention mechanism. So we'll see step by step how, then you'll be able to figure it out, yes, why this attention mechanism, and why on this, why the entire artificial intelligence is actually relying on. So the use case is translating from one language to the other. So this is one of the most famous applications you can see in the current day world. So there is no person who doesn't use translator. For example, let us say a Google translator, right? So English to French using attention enhanced encoder decoder models, sorry. Benefit is attention. See carefully here. See the benefits, what exactly, how it is actually using. So attention enables the decoder to focus on relevant source words for each translated word. Okay. So for this, the attention mechanism works, helps the machine translation to actually translate. Okay. Now let us go to the second example or second use case or second application. So the second use case is the text summarization. Okay. So the first, here you can see generating concise summaries from long documents. So when you imagine now, that you want to translate a huge document or a very big document, right? What is the most important thing when you want to translate, right? So you want the translation to happen, right? You want that particular thing to be in the memory for a longer time. So now best example is summarizing a news article using extractive or abstractive methods. So what is the benefit this attention is actually bringing? So attention helps retain key information from different parts of the text, So now those who are using this text summarization will understand what I'm speaking about. Now you understand that you are summarizing a very huge thing, right? So you want the summary part where you want only the important aspect. Now think logically. You want ideally the model. See, logically, if you think, in a simple way, if you logically think, how it is going to understand, or how it is going to keep a certain things, right, in that entire text, right, how it is basically keeping it, okay, and how it is actually keeping everything in memory, okay, and it is only giving that particular summary which it feels it is very important for you, and not for you, like maybe in that entire summarization part, and what part is very important, which sentence is very important, which is a very key word. This is where the context comes into the picture, because the attention mechanism is applied. Self-consciousness, self-understanding, self learning, self keeping things in memory, understanding the context. Okay, so that is how this particular attention actually works in reality. It's a very, these applications are very interesting applications. How things work, if you dig deep into how these things work, you'll be definitely fascinated and amazed, like how how I am. So it is very interesting, and how things work, like the application of the long attention, or whether it's Bahdanau's attention, or a normal sequence to sequence model. These are very interesting aspect, and how this machine actually applies certain things. So some of the key things are actually there in action. Now the next important thing is the speech recognition. So this is one of the very important applications. Everything is very important, because I've mentioned only the applications which are very important, and one of the most used cases. Okay, the converting audio signals into text. So this is a thing which is important for every person in their life, whether they are using Google Assistant, whether they are using Siri, whatever the AI agents they are using, let it be anything. So even you are not purchasing a separate assistant, it only let it maybe you're only using a Google Assistant for speech to text. So even then you need attention mechanism. So attention allows audio frames to textual outputs, improving transcription accuracy. So whatever you have spoken, that will be converted into a text, that will be actually kept in the memory to convert your voice into text. That is where your attention mechanism actually comes into the picture. Okay. Now, next is image captioning. So generating textual descriptions from images. So a model describing an image, a dog playing with a ball. So visual attention mechanisms focus on relevant image regions during caption generation. So for every image you want to generate a caption, you are going to use it. I think this is one of the applications which everybody will not use, but it is also a important application, let us say. Next is question answering. This is the very important one, and very highly used application. So extracting or generating answers based on a question and context. So what is the capital of France? So it is Paris. So attention helps pinpoint the most relevant context parts that contain the answer. Okay, so this is how, so how it is able to pick, that is where we give the context. Okay, so that is where I showed you how you can give a context, and from that, if when you ask a question, how it is able to pick. Okay, it has the context, whatever you are giving, right? That is why it is being trained on multiple things. Please understand that, right? The next thing is dialogue systems and chatbots. So building a conversational agents that understand and respond, appropriately. So virtual customer service agents benefit is to maintain context and relevance across multiple dialogue turns via attention. So next is code generation and translation. So the translating code between programming languages or generating the code is a very important aspect, right? So converting Python code to Java or generating SQL queries from English prompt align tokens and logic effectively without two different syntax. So this code generation and translation is very important. First of all, generating code is one important aspect. On top of that, if you want to convert a certain, you want to convert a certain, code into one language to the other language, this attention mechanism also helps you to do that in a better way. All right. Okay. Okay. All right. So yeah, next is speech to text. Sorry, text to speech. Sorry, we have already seen speech to text. No, next we are going to see the text to speech. Now, what is the use case here? So generating audio from text, right? And example is Google's Tacotron model. Okay, so attention maps text characters to speech features for realistic output. All right. Next is handwriting recognition. So converting the handwritten input into digital text, right? So this many of you would have tried, tested, and used, right? So example is stylus or scanned notes converted to digital documents. Attention allows better alignment with strokes and characters. Okay. Next is sign language translation. So translating sign language videos to textual descriptions, live sign language interpretation tools. So these are some of the applications you would have seen in many applications nowadays in the real time. So attention helps the model focus on crucial hand gestures or facial cues in video frames. So this is the main impact. Okay, now why this attention matters? Now, handles longer sequences better by dynamically focusing on the relevant input parts, improves interpretability so we can visualize attention weights to understand model decisions, boosts accuracy in tasks requiring alignment between input and output elements. Okay, so now let us first also see what is Bahdanau's attention. Then let us go to the practical part of understanding a sequence to sequence model for attention, for using an attention mechanism. And along with that, let us also understand that how this Bahdanau's attention also is implemented into the attention mechanism. Now, what is this Bahdanau's attention? So it is an additive attention mechanism which allows the decoder to attend to different parts of the input sequence. This was basically introduced in 2015 by Bahdanau, but this was upgraded. Initially it was launched in 2015. So why I'm telling initially, because when the the transformer model, right, has actually been introduced, let us say, things have turned, right? So things have changed, I would say, changed. So the impact of Bahdanau's attention has actually changed with the implementation of a transformer. So attention is actually not like a simple encoder and decoder. So your normal encoder and decoder used to use traditional LSTM models, right? So LSTM and RNN models. So, and those things were actually good. Okay, see, I'll tell you one thing. It was actually good when RNNs and LSTMs were there. It's not like they are actually bad. So they are not actually bad. So in a very simple way to understand, uh, you know uh, things got bit better. Okay, things got bit better in a easier way to understand, right? So right from the normal encoder to decoder, right? Where these LSTMs were performing. LSTMs are actually, trust me, they are wonderful. Actually, LSTMs is a big breakthrough. RNN is only a groundbreaking. Recurrent neural networks is only a groundbreaking invention. Because I worked a lot with RNNs, so they were really good, really good. But when we see encoder and decoders performing using this attention mechanism by using a transformer, these RNNs and LSTMs look, just simple. Because the upgrade was like that, right? The upgrade was ridiculous. Like it was too good, too good of an update, coming to the transformer. Even this Bahdanau's attention was actually transformed, especially when with the invention of a transformer. So there is a lot of changes. What happened from the regular, from the regular, from the regular attention. Sorry, from the regular this Bahdanau's attention to the implementation of a transformer. So let us see. This is the a simple example. Okay, I feel it's a very simple example to understand. I was searching for a very good picture to make you to understand how this how this actually Bahdanau's attention works. Okay, so this is one of the very good pictures. I thought it would be very obvious, because these are basically the recurrent networks. So in the encoding, this basically takes from the sources, goes to the embedding layer, and then to the recurrent network, then to the state, then it becomes go to the targets. Okay, so this was actually the ideal picture. Yeah, yes, yes, Yuri. So things have, in a simple way to tell, I cannot, I was not able to justify 100%, what exactly you asked, but I would, probably, while maybe, explaining the practical part, maybe, I can do justification to your question. I feel, I feel, I've not justified enough to your question. So, I'll try to give the, best possible answer for that, when we go to the implementation part. So I'll take one, while explaining also, I'll just go with, how the implementation is done on the whole, because a lot of people might feel it bit difficult. So I'll try to just simplify it and just tell you that what it is actually doing. That should be sufficient. That should be sufficient, because how these AI agents are able to process things, and how these are able to capture that is enough for you, because you're not going to write, that piece of code, and you're not going to develop anything. So yeah, something like that. Yes, yes, yes. Yeah. Mhm. So I think you're asking like that. Probably you would have worked with RNNs and LSTMs, probably. So that is why you're able to relate things. So those who have worked on RNN and RNN, this now, I hate to say that traditional RNNs, because when RNNs came, they were groundbreaking technology, in deep learning, especially in TensorFlow and Keras. So, keeping that in mind, I would say that yes, it's a very good, groundbreaking invention, especially to understand, right? So in that way, we can actually think of basically about this attention. And one more image, I was just looking also to actually share some formulas. Then I found, I was just searching for images. Then, I got this image. Okay, I just took it from ChatGPT. So it was very useful actually. This was actually, easy for me also to just explain to you. See how this works. Okay, so attention is done. Obviously, this is a deep learning model, correct? Yes. So this is going to use, especially to decode, it is going to use previous states. Okay, so many of you, if you are aware of this, especially, there is one method in stochastic process which actually uses the previous states. Okay, and I'm not exactly remembering the name. Okay, forget about it. No issues. So this actually, in a very simple way, this is basically directly related to the stochastic process. Okay, Markov process. Yeah. Now I am able to remember, recollect. So it's basically related some. It's very similar related to a Markov process. Okay, so I think, based on the Markov process only, this fellow Bahdanau would have actually made his modifications, because whenever I when I saw this, when I was learning this Bahdanau's attention, I felt this is very similar, because what happens is in Markov process. Okay, so there are two things: one which is dependent upon the previous states, one which is not dependent on the previous states. But here what happens in the Bahdanau's attention is present state actually depends upon the previous state. Okay, so it only depends on the previous state, and now the previous state will depend upon that before previous state. So like that, the context, uh, the context, the I would say, in a very simple terms, that the context or the nature, right, and the sequence, right, how things are actually, happening, and what exactly that compilation or what exactly it needs to remember, right? So that particular thing is kept in memory. So the content, I would say, in a very simple language, we can say that the context is kept in memory. So I think that should be sufficient for you to understand, in a simple way. Let us not complicate it too much. So already the model is very complicated. So things like the context will be kept in the memory by the previous state, and that context will be used for the present state. So like that, what is happening is one step is keeping the previous things in memory, and the previous thing is again keeping the previous one in the memory. So like that, it is basically holding the long sequence by using this tan h function. So hey, tan h is nothing but a hyperbolic function. Okay, basically we are going to, most of the, even we have the tan h, this activation function, right? So here we are basically using the softmax, but the function which these previous states are basically using is basically a tan h function. So in that, again, they're going to use the context vector. So I told you, the vectors. So there is actually one particular concept which is called as, vector. All the see, so what is a vector basically is, see, especially what happens, I'll tell you. Particularly for a numerical value, let us say a numerical value, basically it's you in a vector you can only put a numerical value. See, remember, a very small thing. I'll try to make it very simple. Okay, let us not dig too much or complicate. So in a very simple way to understand, this particular vector. Okay, this particular vector, this particular vector can only hold numerical values. Okay, and these numerical values, okay, so things can, these vectors can only hold numerical values. But now when we talk about text data, or when we talk about data which is in a categorical form, right, so that isn't where we are going to go with the string indexer, we're going to do the one-hot encoding. So all those particular procedures where you are going to convert the categorical variable into a numerical variable, let us say a gender. So male, female. So male 1 and female 0. So you're going to give, or you're going to do that string indexer or one-hot encoding. Then you're going to convert that categorical variable into a numerical variable. That particular variable, then only you can put into a vector, because you cannot put male female into a vector. It is very difficult. It is very difficult to put. That is the reason we are going to use a string indexer and one-hot encoding, because let us say all these models, especially when we use big data, for example, like a PySpark, right? So all these models, especially, can only process numerical data, and also all these features should be put into one vector. Okay, on that mechanism, this vector will actually hold those values into a all the features will be held into a vector. So that is what and here you can see the weighted sum. So weights are nothing but the importance given to each particular scenario and context. So scenario, and what is context? What is context and scenario? It is basically giving importance to each word. Let us say it's word. Okay, let us say it's a sentence, or it might be a word, it might be anything. So each unique importance, what we are giving actually becomes this weighted sum. So all these weighted sum are then combined. Okay, and now the fourth point, you can see that the context vector CD is combined with the decoder state to predict the next token. That is how the prediction is going to happen using the Bahdanau sequence. So it's a very complicated model. Actually, it's a very, very complicated model. The functioning also is pretty, using this only, your current AI agents are actually performing. Okay, so this is a very, 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 very important aspect. Okay, so now let us just try and understand that how we can see the practical part. Okay, so yes, I think I somehow I hope I have just given a clear overview, because this is bit out of the I can understand it will be bit out of a normal context. Okay, yeah. So any questions if you have, you can you can ask. Okay, so I'll just give you a couple of minutes, then we can go with the practical part. So you can just ask. Uh, okay, I'll answer that question. Just give me some time. I'll answer your question through my practical approach only. I'll tell you an answer. Yeah, because I can that's why even in the applications, I just took that particular example. For example, you're using Google's translator, correct? So you're using Google's translator. So you're converting from English to French, or English to German, or let us say from Kannada to Telugu, Telugu to Hindi, Hindi to Malayalam, Malayalam to Bengali, Bengali to Oriya. You're converting it, right? Yes, you guys are converting using the Google Translator. So you are using Google Translator. That means you are using it is translating using the Bahdanau's attention only. So I cannot give you a better use case than that. It's a very, very standard and an excellent use case. So that is what you can see the Bahdanau's attention in action. So in one way, it is that. So any other questions? Yes. Yes, quickly. I'm just compiling this. In the meanwhile, you can just ask me. Okay, fine. I think it's clear. I'll just share my screen. Okay, we'll start with the attention mechanism. Okay. All right. So let us now try and understand with the Bahdanau's attention. Okay. Now, the first important, sorry, let us see the basic sequence to sequence model first. Then we'll go with the Bahdanau's attention. Okay. So that should be easy for you to understand. So that is why I have taken in that order. Okay. So it will be, easy for you guys to understand. All right. Now, the first important task here is to implement the sequence to sequence model using the attention mechanism. Now, to understand the attention in a very simple way, we are going to use the PyTorch. Okay, so PyTorch is a very important library, especially which is used for doing this kinds of tasks. For example, like a transformer kind of application. Now, here you can see that this torch.nn function, which is basically a neural network. Okay, so nn is nothing but a neural network. Okay, so this basically uses the torch and the nn as nn. So torch.nn is basically the implementing the neural network. Now, to understand that in a very simple way, the first important thing which we are going to use is the init word. So init, here you can see init function. Okay, so here you can see here in the init. So init is nothing but a self constructor. Okay, so constructor is nothing but a I can say it's like a trigger to do something. Okay, so an action, something which can be applied, right? So into action is basically a constructor. Now here you can see that we are defining a few constructors. So not exactly constructors, they are basically parameters. So parameters in an easier sense that something which we are giving as inputs is basically a parameter. Okay, so that is what basically a parameter is. Now, the most important thing is we are going to define a few things. Okay, so to understand the sequence model, first of all, we have to give the input. Okay, so then we go with the encoder model, then we will decode, because basically this transformer is a encoder and a decoder model, right? So now here we are defining a few things. Okay, so here the most important things are self, input dimension, embedding dimension, hidden dimension, n number of layers, and dropout. So clearly I have mentioned what is this. So self is nothing but a constructor which is actually defined. It's a self, it is for self-learning, you can say. Those who are very new, you can understand by something which is a self-learning mechanism. So for that, we are giving the self. Then you have the next one, which is input dimension, which is the size of the vocabulary. Okay, so that means the amount of words which you are giving for the training. Next is the embedding dimension, which is the size of the word embeddings. Okay, so next is the hidden dimension, which is the number of features hidden in the GRU model. We are taking the GRU model. I'll tell you that also in detail. Okay, don't worry about that. So next is the number of layers. So number of layers in the GRU model. So next is the dropout. So dropout is basically used where something, to prevent this overfitting, we are going to use the dropout. So any layer is going to overfit, that particular layer is going to be dropped. Okay, that is how you can actually remember. Okay, now we are defining certain embeddings. Okay, in just a simple way, I'll just tell you. Okay, basically what we are doing is we are going to define a particular encoder model. Okay, and this encoder model will have certain parameters. Okay, so these are the parameters which are given for the encoder model. Now, what this encoder model will do is it will train. It will train on a certain input. Okay, so that input will be converted into a vector. Okay, so clearly listen. So that what encoder you are actually giving, that will be trained into a vector. Okay, so that will be put into a vector. So this vector will have a certain shapes and sizes. So length of the vector, like that means the let us say the let us say the length of the vector or the shape of the vector, right? The batch size. Batch size is nothing but the sample size. Okay, on which it is basically going to sample, and number of layers in which a number of deep learning layers, or how many input layers which are going to be put inside, right? So all these things we are defining one by one, one by one, one by one, so that the model is going to be applied. So this is the basic encoder model which is actually done. Okay, I'm not going into very much detail. So those who are computer science people, those who not even they don't know Python, so it will be very difficult for them. So anywhere I'll share this. So those who are very much aware, you can go step by step. Okay, so anywhere, any line of coding also, if you don't understand also, you can ask me. Okay, that is why for simple understanding, I've added tons and tons of comment. Actually, the coding part is very less. You can see here, if you remove the comments, you will understand. It's only some, here 2 lines, here it is 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14 lines of code only it is. But it looks like some 30, 40 lines of code. Yes, it is because of the comments I've added. Okay, so I've added comments because it is very easy to understand, for people, because to share with students also, it will be easy, when I add comments and share it with you guys, right? So that is why I have actually added these comments. So it will be useful for you, and it will be easy for you to understand. Just all right. Okay. So in that aspect, it will be easy for you to just go through. Okay, so you can go through it later and you can ask me also. It's fine for me. Okay. Now next is we are defining a decoder model. So we have just done the encoding part, right? So we have done the encoding part. Now the next important thing is to do the decoding part. All right. So we have to do the decoding part. Now to decode, the most important thing is only the relevant parts which are very important are decoded. That is what this attention mechanism is famous for. So if you read this line, you'll be able to figure it out. So the sequence model, it is basically, or this attention mechanism is basically helps you to convert the relevant parts, especially into the input sequence during the decoding part, or to decode it back again. Now we are using the important softmax here. So in the image also you have seen, no? So I have used the softmax. I'll show you page. I have mentioned it actually. Okay, fine. I'll just go step by step. I'll tell you. Yeah. All right. So here you can see that the attention what we have encoded there. Okay. So that particular encoder, what we have done in a in a simple way. Here you can see what is attention. See, it is showing this. Okay. Yeah. So base class for all neural network, your module also subclass. Okay, not useful. Something it is showing. Okay, right. So these are the important things which we want to be decoded. Okay, from the encoder part. Okay. Now we are using the forward pass. You can see here we are defining that particular function, which is a forward pass. Okay, so forward pass and backward pass, you have both. And here, yeah, sorry, I have not given the softmax, but I have used the tanh function. Okay, so this tanh function is basically a linear layer. Okay, it's basically an activation function. Okay, so I told you, you have softmax, tanh function, like that. We have multiple, we have a lot of multiple, activation functions. So activation functions are basically nothing but statistical functions, or you can say a mathematical or a statistical function, which is basically built upon, right, from one particular function, which is basically implemented from one particular layer to the another layer. So, implementing from one layer to the other layer, it is very important that you, because these deep learning models all contain hidden layers, right? So since these contain some hidden layers, right? So each layer, right, from one layer to the other layer, you have or you need one particular mathematical function. So that particular function is basically called as a activation function. So in this case, you can see that you have given the tanh function, and here we have concatenating the hidden state and the encoder outputs. And now that particular tanh function is basically applied onto the attention mechanism. Okay, so here you can see that we have mentioned that this attention mechanism is a linear. Now, somewhere I mentioned here, yeah, I mentioned that it is a linear. Yes, yeah, you can see here. Okay, now what exactly is going to happen is it is going to by step by step. Okay, so each by step it is going to, okay, I just reduce a few code looks too much big. Okay, yeah. It should help you a bit. Yeah, okay, so a few comments I have reduced. Okay, all right. And now once we have actually applied this linear model, right, and we have applied this tanh function, okay, and after that, to apply this attention, once it is applied, to concatenate, here you can see concatenates each encoder hidden state with each decoder hidden state. Okay, so it is going to identify that what is a hidden state, what is a decoder model. So applies linear layer and a tanh activation function. All right, so this is what basically it does. So comments we can move to the starting, but we cannot move the code. Don't move the code. Okay, yeah. Okay. So if you want gap, you can actually give, no issues. Okay, so now in a very simple way, okay, so in a very simple way, to understand, we are exactly decoding it back what we have encoded. Okay, now how does it actually fare? In a very simple terms. Okay, even a person who doesn't know anything also should understand. Correct. So in a very simple terms, what it is going to do is it is going to identify that which has to be decoded back. Okay, so that is what we are going to do. Okay, so that is why we have given the self-learning part. Now on the variables, what we have made it to learn. Okay, so what it will do is it is going to learn on itself. Okay, now what exactly is required to put it back, okay, or to decode it back, okay, that particular things will be kept in the memory. That particular things will be kept in the memory. So right from the length, okay, right from the how much of dimensions are actually required when you are training something. So each individual or each aspect will be actually kept in the memory. So that is in where your attention mechanism will actually help you to understand and put it back. So for that, we are going to use the activation functions. whether, I told, I have used softmax. Yeah. So immediately, I couldn't find where it was. So applies the softmax over the, length to get the normalized attention vectors across the timestamps. Because softmax is definitely used in the sequence to sequence model or a Bahdanau's attention. So definitely I was, skeptic. Suddenly I couldn't find it, right? But definitely we are going to use the softmax softmax activation function for the decoding of the attention mechanism. So that is one of the key aspects in which we are going to apply. Now we are basically applying the GRU's model. Okay, so GRU is nothing but a gated recurrent unit. Okay, now this GRU model is basically applied. Okay, and this forward pass and backward pass is basically applied. Sorry, backward pass is not there. We are only applying the forward pass. Okay, and in a very simple way, yeah, the code is very big. I know. That is why I told you no need to remember anything or something like that. You can just understand that how. That's why you can just go through the comments. Okay, so this comments will actually help you to understand in a very simple way. So now what you can actually do is from the from the very basic things. Okay, so from the basic things that how it has actually trained on. See, that is why wherever you can see I have put the self. You can see carefully. This self indicates the self attention on which see self at the rate of decoder. That's what only I was telling you. So it will identify, that is the capability of this GRU model inside the attention mechanism. So what it will do is it is going to identify that what is the input, what is the output which is required, and what it has to decode in a very easier way, again back what it has encoded. Okay, so all the things which are actually required to keep in memory, especially whatever is required to be kept in the memory, that will be kept in memory. Okay, and it will be written. Now you can see that when we are basically see the output, the prediction part, you read this comment, you'll be able to figure it out. So unnormalized scores over the vocabulary, updated hidden states to be passed to the next decoder step. So once it is basically done, we are going to overall apply the we are going to apply the encoder and decoder models together, right? So that we are going to do here in the the sequence to sequence model. Okay, so I'm trying to just reduce the here I've added the okay. So here you can use that, you can use the CPU or GPU, okay, for model execution. I told these particular deep learning models use the GPU for faster processing. Now here we are using this teacher forcing ratio. This is one of the forward pass I can say a decoder thing. See here, probability to use a ground truth token as the next decoder model. This basically this teacher forcing ratio. The name looks funny, I know. So this particular model is basically going to process the decoder much faster. Okay, so that is the main aspect of it. Okay, now combining both of them, and we are going to do the prediction part. Okay, so once this particular attention, what you have actually given is how things can be kept inside the attention. That only we have defined. Okay, how to remember things and to keep in attention. So that only this encoder and decoder model is. Okay, so that is why only when you are building an AI agent, there is a lot of coding part which is actually behind it. Okay, it's not as simple as it looks. Okay, so there is a lot of things which are actually attached to it. Now, once this particular encoder decoded model we have actually defined, okay, the next important thing is we are basically testing that attention. We are basically testing that attention. Now that testing doesn't mean just like you just give some input and test. No, it's not like that. So we are basically now, since we have defined the encoder and decoder model, the next important the next important step is basically to train the loop and include defining the loss function and the optimizer. So loss function is nothing but the difference between the the actual label and the predicted value. So this is basically called as a loss function. So in a very simple way, you can remember it is like the difference between the actual and the predicted value. So this will be defined, or this has to be very less, right? So if it is very easy, for example, if it is very less, for example, the difference between the actual and the predicted value, if it is very less, so that means the prediction is actually really good, right? So the prediction is really good. Now it is very important. It is very important for us to have that loss function very less as possible. So the next important thing is, that is very important, and also along with that you have something called as an optimizer. So optimizer is basically nothing but something which is basically used to optimize. That means the best possible solution, okay, which is basically which it is supposed to give, right? So the optimizer, for example, we are going to use the Adam optimizer, and that is one of the best optimizers which actually you can have. Now here we are defining the Adam optimizer. See, adaptive momentum sampling, something is there. So Adam is a very famous optimizer, okay, which is actually used very highly. And here to compile this, you are going to use the this particular code you have to mention, because if there is a CUDA core GPU, it is going to compile using the CUDA core GPU, or you can say GPUs. Especially if you have GPUs, definitely you will have CUDA cores. Okay, so if that is the case, you can use the CUDA cores, or you can use a normal CPU for compilation. So that is why I've added a comment also. So choose the GPU if available, or else go with the CPU, because these are very high-end models. Okay, and these models are, it's not just like sorry, these models are not just like normal CPU compilation. They require huge amount of compilation speed and these CUDA cores. Okay, and that is why we have to give this particular, because this application torch, which is the PyTorch, so basically it is relying heavily on GPU. Okay, so it is very important that we give it whatever you actually need. Okay. Sorry. And here you can see there are a few things which I have actually defined. So all of them I have mentioned here in a very easier way. And the first important thing in this is, I have given the cross entropy loss. Okay, so cross entropy loss is basically it is basically a loss function. Okay, it's a kind of loss function which is actually used mostly in your machine learning algorithms. So apart from that, this is this is basically a kind of loss function which is used in many algorithms, and we are going. It's a very strong loss function. So how it is basically calculating the loss between the predicted and the actual value. So that is why we are also going with the most common loss function, which is the cross entropy loss. So in that way only, even I have defined that. Okay. Now after that, especially once now see here, what I told you, we are basically combining both the we have combined here. See, just we have combined both encoder and decoder. The next important thing is we are going to train it. Okay, so for training loop, and we are defining the loss function in the optimizer. So now what is expected? You just understand that here you have the input as 10,000, output as 10,000, and encoder dimensions are basically 256. Decoder is also 256. Hidden dimensions are 512. Number of layers is 2, and encoded dropout is 0.5. Decoder dropout is 0.5, and attention dimension is 64. Padded index is 1. So these are the individual variables which we have actually given, or we have actually defined. Now, what exactly this will actually do is, it is, see here, I have actually put one particular comment here. Okay, so what is this basically comments here? What is going to happen is, it is going to train, okay, it is going to train first of all on what I have given. Okay, on what I have given, it is going to train, because we have already defined the encoder and the decoder model. So since we have given the encoder and the decoder model, it is going to train on that particular encoder and decoder model, and it is going to bring in the best possible value or the prediction, because we are using the optimizer. So Adam optimizer is a, here I've shown, yeah. So for loss function, we are using the cross entropy loss, and for the it is showing, see, cross entropy. Yeah, you can see they made the criterion components across loss between the input logics and the target. So I just told you, in between the predicted value and the actual value. Okay. All right. So that is basically done in a in a very simple way to understand about this this optimizer. Then it is going to find the best possible value. Now, the next thing here is to evaluate, right? So we have basically done the encoder part, then we have done the decoder part, then we have combined both encoder and decoder part. That is one thing. And after that, what we have done is the training along with the loss function and the optimizer. So this is what on the whole we have done. So that is what we have actually done till now. Now the next important thing is the evaluation part. So coming to the evaluation part, we are going to evaluate the metric or the model which we have actually developed for evaluating the for evaluating a particular in a simple way, how to tell to evaluate this, we have one particular model. Okay, we have one particular model which is called as BLEU, BLEU. So this BLEU is nothing but a best linear estimator, unbiased estimator. So we call it as BLEU. So this is basically used to evaluate the the model's prediction. Okay, so especially this BLEU is used for translation tasks. Okay, so this particular BLEU is basically going to be used, okay, and we are going to evaluate it. So this is what the model is. Okay, so this best linear unbiased estimator or BLEU, what we are actually going to apply. So this is basically used for textual data. This is basically used for textual data. And what this is going to basically do is, it is going to evaluate each and every aspect. So basically, what is evaluation? You tell me, evaluation, what is, or evaluating a model, especially when it comes to such thing, sequence to sequence models or this attention mechanisms. So what are these what is this evaluation is going to do? Tell me. So this is basically what it is going to do is, it is going to find out the best possible it is going to find out the best possible way, right? That how yeah. So it is going to find out the best possible way that how it is actually able to predict the values. So that is what basically we are calling it as what we are calling it as evaluation. So this algorithm basically uses this teacher forcing mechanism. Okay, we have defined there teaching forcing ratio. You remember? Yes. So this is basically using this teacher forcing. Okay, and to predict this, we are actually switching off. Okay, because we have defined that teaching forcing ratio there. I think we have given around 0.5, if I remember, because that was the learning rate. I remember giving for the teacher forcing ratio. So here in this particular thing, we are basically not using that, and we are actually giving and training the corpus. So here you can see that this best particular values. Now, if you see that the calculation or the evaluation is basically done using the BLEU score. So this is basically how the attention actually keeps in memory. So for this, how to, I have shown you that how we basically define, okay? In the same way, I will show you an example also, how it can actually be implemented also, okay? So how it can be implemented also, that also I will actually show you, okay? Um, uh, uh, that I'll show you with one example. So it will be even more easier for you to understand. So yeah, in that way we can just try. Okay. So what we'll do is now we can just go for a quick break and we can come back. Yeah. So if you have any questions, you can just post it. Okay. I know it's a bit on the tougher side. I can understand. You know. So yeah, it was like mostly in the coding part, but the main aim is for you to not don't need to remember anything. The most important thing in this particular thing, what I've actually given you is the most important aspect is in this such thing is how an attention mechanism is actually defined, okay, and on what parameters it is basically using, how it is actually defined, how you can actually process the things. That is what my aim was to explain to you. It's not about you learning the coding, okay? So those who are into the coding part, into AI and all those things, as an AI engineer and all those things, you'll be definitely yeah, yeah, it's a bit on the complicated side. I know that. So I'm not expecting you guys to completely just yes, super returns, we can code like this. So it's not possible, okay? Even I have taken the code from multiple areas. I have modified a few things, so even it was a lot of headache for me also to do on that. So it's not a very easy task, so I'm not expecting you guys. So just try to understand that one thing is when an agent actually does a few things, right, it requires a few things to be done, especially when it is doing the attention part, okay? So on that particular aspect, this is basically this is basically followed, this procedure is basically followed. So just to uh, make you aware. This explanation was more of a like an awareness rather than you reading by hearting and doing the coding part. It's more like an awareness where you can understand that how this attention mechanisms actually work in reality. Okay, on what parameters it is defined, what how the encoder model is actually defined, how the decoder model, how the combination is basically done, how the training is done, because you need to train it to test it, right? And before you have to use the this loss function models, then you have to give the optimizers. Like that, there is a lot of hangama which has to be done when you have to define a particular attention mechanism. So keeping all these things into consideration, that is how an AI agent will actually perform. That is how it is basically going to be implemented, because it is going to follow all these. On this only, the basic and AI agent will be actually developed, because it has to see, we are expecting so many things from a particular agent, right? So how do these so many things, this attention mechanism, the context based learning, how all these things will come, just from the sky it will not come, right? So we need to develop, we need to build a model in order that it has to keep things in memory and it has to process. So for all these things, this kind of importance, or this kind of mechanism has to be given. So yes, that is the that is the way it is. So yeah, we have to accept it and we have to go. All right. So it's been usually I give it at 8 only, so it's been very late. Just I also need just a couple of minutes, so I'll just come back quickly. Okay, so please take a break. Yeah. All right. So fine. So I think you are very clear on what we have discussed. Attendance link will be shared, Vaishnavi. Please wait. So just be patient. Just be in the session. You will get the link. Okay. So at a certain time only it will be shared. So you have to mark at that time. Okay. Right. So let us go to the next one quickly because we are having only some 35 odd minutes. So we have to finish the Bahdanau's attention also. Okay. So then tomorrow we can go into the applications entirely uh, you know uh, of especially implementing these agents using the attention mechanism. So directly we'll apply a few things. Let us just discuss a couple of use cases, a couple of agents. Let us build and try and understand. Okay, so that is how we can actually function. Right. So let me share yesterday's link. You will not, it will not be shared. So if you're not able to mark, it's cannot be shared. In today's, you can only mark for that respective day. Okay, so you cannot mark for the previous class. That will not be shared. All right. So please don't forget to mark today. Okay. Pakshal. Okay. Yeah. So please do that. All right. So let me share the next one, which is the Bahdanau's attention. Let me share quickly. Yeah. All right. So we'll start with the Bahdanau's attention. Okay. Now, to understand Bahdanau's attention, we are going to use the TensorFlow. Okay. So there we have used the torch, PyTorch. We are going to use the TensorFlow. Okay. Now, uh, now let us say that now let us try and understand that how we can actually implement this Bahdanau's attention. Okay. Now, the most important application, especially now, is to to execute or to make sure that how this attention mechanism actually functions. Now, and we are already familiar with. Okay. Sure. I will send Manasa. Please wait. Be in the session. I will share. Okay. So to understand this, the most important thing is basically trying to understand the most important thing of attention is applying the encoder and the decoder part, right? And we know that applying the encoder and decoder is what the main function, or I can say the main functionality, especially when it comes to the especially when it comes to the attention mechanism. So here we are basically, I would say defining a few things. One is the layer part. So layer is basically for the number of layers. Then the input is what the what we are giving as a Keras. So Keras is nothing but a framework. It's an application which is used to implement the TensorFlow. Then we are using the dense. Okay, so here we are going to use the dense, that means the fully forward neural network. Okay, feed forward neural network, and here especially we are using the forward forward mechanism. Okay, so we'll also see a bidirectional approach, which is a BERT. So what I'm planning is also to implement the BERT mechanism with a use case. So we'll apply BERT mechanism with a use case so that we can see the bidirectional approach also. I will all probably tomorrow or day after tomorrow we'll see the BERT approach as well. Okay, so it'll be good for you that yes. So this kind of approach, how things work in the attention mechanism also, you'll be able to figure it out. So the next thing is the GRU. So GRU is basically a type of recurrent neural network. Okay, which is basically so GRU is, I told gated recurrent unit. Okay, so it is basically used for the sequential data. Pallavi, I will share. Please wait. So yesterday's I'll not share again. I've already shared. it will be uploaded in your LMS. Okay, so it will be there. Okay, so please wait on that. I'll share it. Okay, cool. So today in the PPT, it will be very less. It's more of a practical. Only the use cases or how this attention mechanism is basically used. I've just mentioned only a few things. All right. So now talking about how this particular embeddings we are going to use, or how we are going to create a dense vectors. So I told how this vector is basically created inside. Just give me a minute. Yeah. So how this particular this embeddings are actually done. So word embeddings, I told that how it is going to be mapped and how it is going to be converted into a vector and how it is going to be put into a vector also. Like which kind of thing, and once it is converted, how it is basically putting into a putting into the form of a basic vector, then how it is actually analyzed. Because I told you the categorical variables are basically converted into using a string indexer and one hot encoding. So for that, we are using this embedding layer. Then we use the attention mechanism, which is a sequence to sequence approach, what we are which we are actually using. Now, the important thing is I already told you about the Keras. So Keras is nothing but a framework. Okay, so which is basically used. Now the NumPy is basically a library. It's a very small library which is used for numerical operations. What happened, Habib? You are it will be updated. Sorry, it will be uploaded in everything, whatever it will be uploaded in your LMS, man. Don't take too much tension and don't think too much. Yeah. Attendance will be shared. Attendance will be shared. Everything will be uploaded in LMS. Don't worry too much about things which are, all the external things. Ombre Baba. First, focus on things which are very important. Okay. So you can worry about things which are not important later. Okay. So please. No. It is separate, Kenisha. It is separate. Yesterday I've discussed about the agents. I have discussed of a few basic examples of agents, how these agents can actually be, how these are actually formed and how they are actually, created and how they actually perform. That is what we have discussed. Now, what I am discussing is basically about the, on what basis it is going to work, how it is working, that working, how it will function, its working procedure, I can say in a very simple terms, its working procedure, how it is going to function literally. That working procedure I am actually discussing here. Okay, so I think now it is clear for you. Okay. So I think uh, think it's fine now. Okay. You need not remember it well. Okay. So it is more like a working procedure. So yes, if you want to build an AI agent from scratch, if you want to completely build, okay, if you just want to use an AI agent, you need not, remember all these things, need not understand that much. Just working procedure for a basic understanding, it is enough. Yes, yes, yes. Yes, because on these things only an AI agents are actually created. Yeah. All right. Okay. Now, let me continue on this. Here, actually, you can basically see that we are basically using the encoder and the encoder and the decoder models here because that is how the Bahdanau's attention will be actually defined. So the first thing here is basically the encoder model. Okay, and for this encoder model, basically, I am giving the custom TensorFlow and the Keras approach. Okay, and the same way how a default constructor is actually created into the sequence to sequence model, the same way we are actually creating a default constructor here. Then we are initializing the construction for the constructor for the training purpose. Okay. Then these particular instances are basically stored in batches. Okay. And then we are going to apply the embedding layer. So all these things we have done in the sequence to sequence model. Yes. And here, next step, what we are actually trying to do is we are going to apply these things. Wait, I'll move this forward. Okay, so it will be easy for you. Okay, so already the code looks too big. Yeah, so you might feel bit on the heavier side. Okay, so those who want to learn, okay, those who just want to understand, it's fine. I can understand that it's a bit too much for a few people. No issues. Okay, yeah. So now to understand the most important thing. All right. Yes. So in a clear way, in a clear way to understand about, this especially where we are going to apply, this encoder part first, right? And in this, in this particular thing, we are going to store a particular instance here. So that is what this particular instance is about. So we are going to store here. So clearly you can see that these are the two instances which we have created for self-learning for the model. Okay, so okay, so this is what is created for the self-learning of the model. Then we are going to give the embedding layer, and this embedding layer is what it actually creates to become a vector, a dense vector. You can see here. See, embedding layer to map word indices to dense vectors of the size of the embeddings. Okay, so after that, we are going to use this GRU units, okay, gated recurring units, to basically train. Okay, so self understand that which kind of things has to be, learned and which has to be returned. So that is what this, especially the, see, I have actually mentioned in a very simple way. Okay, so yeah, this particular line will give you a better understanding. Okay, so what exactly I have done in the encoder procedure? So converts the word indices into a dense vectors, then feeds them into a GRU to learn temporal dependencies, then returns the sequence of hidden states and the final hidden state. So this is the main thing what has actually been done in the piece of code. So the next thing is I am defining the Bahdanau's attention. Okay, this Bahdanau's attention I am defining using the Keras layer. Okay, so I'm defining Bahdanau's attention using the Keras layers. Okay. Okay. Now here the same way I am basically constructing the constructor here. You can see here. See this line. This line is very important. So here I am constructing a constructor. Then this units refer to the number of neurons used in the internal dense layers for computing the attention scores. This is a very important line. Now we are literally calling the attention part. You can see here calls the parent class constructor to properly initialize the layer. That is where we are creating the super class. Okay, so which is basically used here. You can see super class is basically for calling the Bahdanau's attention. Okay. Okay. No, I'll keep it here only. Yeah. Now you can see here, once that is done, this is one part. Now we have to understand now step by step. Here you can see there are three layers which we have created, which is the W1 layer, W2 layer, and the V layer. This W1 layer is nothing but a dense layer to transform the query vector. The W2 layer is nothing but a transforming the values. The V layer is nothing but to compute both of them together to compute a score. Then what we are trying to do is we are trying to calculate the query shape, values, everything for all the dimensions. We are basically calculating it. Okay, so this is basically calling the or creating a forward pass. Okay, I told you, forward pass because this Bahdanau's attention, Leong attention, not especially, Leong attention, Bahdanau's, these are basically forward pass. So, bit more advanced with this attention mechanism, you have the BERT model. So that also I will tell you with an example. Okay, a use case, especially I'm going to take and I'm going to explain. So it'll be a better way for you to understand as well. Okay, so now the next important thing is the values. The scores are basically calculated. Okay, so especially here, what we have given here, I'll just put like this. It'll be easy for you to understand. Okay, now you can see this W1 layer, what is created here. This W1 layer is basically, I've mentioned here very clearly. See, this W1 layer is nothing but which basically used for transforming the query. And the W2 layer is especially used to transform the values from the W1 to the W2. Then the next important thing is basically combining both of them and applying the tanh function. Okay, which is a non-linear activation function. That is what this particular thing is about. Okay, so applying both W1 and W2 functions along with the tanh function and along with this self function V, what is defined here. Okay, so that is what that is what basically the the mechanism here, what it is, the score, what it is. Okay, so after that, once it is basically defined, the next important aspect here is, it's better to keep like this only. Okay, yeah. So the next important thing here is to give the attention, a shape. Okay. So I'm just trying to reduce a few things. Okay. I think now you can see clearly. Here you can see in a very this because this is one line actually. It should be in one line. So here, what is the attention mechanism doing here is this basically applies with a batch size and the maximum length. Okay. Then the next important thing is applying the softmax. Okay. So applying the softmax to get the attentions. Okay. and how much attention to pay for each encoder output is what this attention mechanism is basically about. Okay, so this is the main important aspect. So I'm just reducing these comments to one line. Okay, yeah, because there are too many comments. Okay, but I cannot delete any comment because each line I have actually added some important comments. Okay, so that it will be easy for people to understand. Okay, uh, because this is completely new for a few people. Okay, so why it is showing this line? Malicious. Yeah, no problem. Next is defining a custom decoder. Okay, and for defining this custom decoder, we are using the Keras. Okay, so these Keras are basically used also for the decoder models, which we have initiated using the which we have created for the encoder model. Okay, so that is what this Keras for the decoder model also is going to do. Now, if you see clearly, the next thing is this is basically the variables which we have created. So which are created in the encoder model, the same variables I am giving here. I'm not changing anything actually. I'm not changing anything. The same thing what I have actually given. So the same thing only I have basically mentioned. Okay. So now going to the next part, okay. And for the embeddings part, I have basically taken a GRU model, and this GRU model actually uses a certain things. Now see clearly here, this particular comment I'll show you. Okay, yeah. Now see here clearly this particular line. Okay, so GRU layer to model the sequence dependencies. Okay, so this basically returns the sequence to be true. Okay, this basically outputs the full sequence. Okay, and if the return state is the return state is true, because we have two things. One is the return sequence, one is the return state. So if the return state is true, this also returns the hidden state. So that is why we give all true only, because we want to see the return state as well. That is why only we are defining. So without the return state, what we are going to do? So we will give the return state as well. Okay, and that particular thing is basically defined. Okay, yeah. So that particular thing is basically defined here. Okay. Now the next important thing, once it is done, we are going to concat the vectors. Here you can see that concatenation the context vector and the x value, which are the inputs. So that concatenation we are basically doing, and then we are reshaping the outputs. Okay. Now in a very simple way, okay, in a very simple way to understand what exactly I have done here. Now this is what the process which I have done. The most important thing here is I am using the embeddings from the GRU model, which are actually given as a input. So then once it is actually given, I will attend to the encoder outputs with the Bahdanau's attention, combining both the encoder model and the decoder model for basically getting a proper prediction. Okay. Now this is basically outputting with the probability distribution over the vocabulary or the next word prediction. So this is how it is going to be. Okay, which is going to be done. Now let us see the example of implementation now. Here you can see the Bahdanau's attention. So input I have given 5,000 vocabulary words, and for target I have given 6,000 vocabulary words. Okay, and here you can see the word embeddings, which are around 256, and the number of units is 512. The batch size is 32, which is a sample size, and the maximum input sequence length is 100, and the maximum target sequence length is 120. So these are the inputs what I'm going to take for defining the model. Okay. Now, the next important thing is to use the input and the target variables. Okay. Now, in this input and the target variables, okay. So in this input, especially, this is basically creating a random batches. Okay. So this is basically creating the random batches for input as well as the target sequences. Now, each batch here, if you can see dot random dot uniform. So you can see the entire function, which is TF. See, it will show you also. See, it is showing here. You can see here, see, random underscore uniform. That was the function actually. Okay, so that basically create, yeah, this is basically used for uniform distribution only. But in this case, why we are basically using is to create a certain values. That means for, it might be a, an approach where it is going to train a random sample of batches. So for that, we are giving the random dot uniform function. Okay, so it's a very effective and a very important function, which we are basically going to be, which we are going to actually define. Okay, yeah, that is the most important thing. Now, here we are basically defining many inputs, okay, and some of them are basically, which we are actually going to, be defined especially. So here you can see that we are basically using the teacher forcing algorithm, because this teacher forcing algorithm is especially used in the Bahdanau citation. So this is basically used in the Bahdanau citation. And for tokening or for start tokenizing, we are basically using the Bahdanau's attention. So definitely that was a very important application, especially a function which is basically used inside the the model. So once that is done, you can see the encoders, encoders output shape and encoders hidden shape. Along with that, encoders output shape and encoders hidden shape. So what we have defined, it is able to be, it is basically able to put it, into that particular frame. Okay, so that is what this Bahdanau's attention will actually do. Okay, so that was mostly about this Bahdanau's attention. So any questions if you have, to understand more deeply on what we have discussed today for the attention mechanism, I would actually tell you to wait till tomorrow, because tomorrow you will have a like a continuation for what we have discussed today. So it's basically like a for today's. So yesterday's was actually a concept which I've kept it a bit separately. So today's concept we have a link for tomorrow's session, because that is how we are going to apply this, models, into especially we are going to apply this model where you can actually, use it, okay, into the real life applications of building an AI agent. So that particular application I will actually tell you in detail. Okay. So attendance link is already shared. You can just mark your attendance. Okay. So that is one thing. So just about the doubts, if you have, you can probably ask me. Okay. So I'll just share the files as well. Okay. So the two Python files I have shared. Okay. Shh, Pallavi, I will share Pallavi. Oh my God. You are like behind my back. Please, sir, please share, sir, please share. I will share, I will share, I will share. I will share. Definitely, I will share. Okay, you need not worry that much. Okay. So PPT also I'll share, but nothing much in the PPT, but it's okay. What we have covered is the attention mechanism of sequence to sequence approach and the Bahdanau's. Okay. So anywhere PPT I'll be sharing also. But most important thing is the Python file. Okay. So that is the most important aspect. Okay. So because it was mostly onto coding only. What to do? So yeah. So just on anything, something you want to ask, you can ask. I've shared the PPT as well as the Python files. Okay. So if you have any doubts, you can ask me, because in middle I didn't allow you to ask any doubts actually. Because it was a continuous, tedious, explanation part. So it was a tricky part to explain also. Okay, how many times I use it for explanation, still it is always tricky, because yeah, it has a deep down coding embedded in it. So yeah, it is what it is. Attendance link is shared, madam. Sorry, Sanjay. Okay, quite. Yeah. So yes, I'm just waiting for your doubts. So yes, please. Any questions? Yesterday's PPT. Mallavi. Please wait. I'll just check and I'll share. 12. Day 11. Yesterday it was more than PPT. It was on completely on practical part only. So it's not basically. Yeah, I've shared for you. Okay. Yeah, this was yesterday's actually. It was more all agents only. 4 agents we have constructed, and then nothing much in PPT. At least today we had something in PPT. Yesterday it was just I've added a slide practical of so practical part of the entire 4 agents. So yeah, that was it actually. Okay. All right. Uh, yes, ma'am. Actually, I'm done. So if you're there,
Yeah,
I,
I'm there.
yeah, because no questions also from students.
Okay. Yeah, no issue, sir. We can wind up for the day.
Sure, ma'am. Yeah.
Yeah, we will meet again by tomorrow at
Mhm.
7 p.m. Yeah. Thank you, sir. Thank you so much. Yeah, dear students, the material I'm going to be upload in LMS dashboard. Please be in patience. uh, Mainly Pallavi, like when the sir is explaining something, if you ask in the between, it will disturb to sir. I hope you understand. Please be waited. All the materials links have been uploaded in LMS dashboard. Please check over there. Okay. Fine. We will meet again by tomorrow at 7 p.m. Okay. Yeah, it is going to be upload. Okay, so the materials even you can access, you will get a lifetime access of LMS dashboard. You have to be in patience. You will get it. Okay. Yeah. So I hope you all marked your attendance. If not, I have just shared it once again on the chat. Kindly mark your attendance. Okay. Fine. We'll all meet again by tomorrow at 7 p.m. Thank you all. Thank you for joining. Good night, everyone.